Solar power is one of the most important and quickly growing sources of renewable energy available today, but one of the limiting factors is that hot solar panels are less efficient, and when exposed to the sun all day they tend to heat up and their performance drops. This heat is carried off mostly by the air around the panels, and the coefficient telling us how fast this cools the panels is the aptly named convective heat transfer coefficient, called H. During the summer of 2017, this sensor tower at a solar PV plant at the Denver Federal Center collected data on a number of variables, including wind speed, direction, temperature, and relative humidity. The heat transfer coefficient was calculated based on an energy balance model of the solar panels, and all this was sorted as a collection of 1-minute averages. A more accurate and more expensive wind speed and direction measure, the sonic data, was also collected from the sensors shown on the right of the image. Our goal for this project was to train a model to predict the heat transfer coefficient based off of the data which was collected, with the hope of better predicting energy produced at solar power plants given certain conditions, as well as to potentially provide insights into how to maximize the cooling of solar panels and thus efficiency. Shown here is a histogram of our observed H values. Based off of the spread of the data and our accuracy in calculating H, we decided a prediction within plus or minus 2 of the true H value would be a correct prediction. Our secondary goal was to help provide some insights into whether the sonic data sensors are worth the extra money and effort. The collected sonic data was processed using the UTPAC program as well as some MATLAB code to produce something legible with us. We began with approximately 1.7 million lines of data per day, and distilling it to something useful was quite time intensive and complex. So to determine if it's really worth the extra money for the sensors, and time and computing power processing it, we'll try running some models with and without this data. Once the sonic data were processed and the sonic and full data were filtered to remove parts where the instruments weren't collecting, or had collected insufficient data, we were ready to build our models. The cleaning is shown here with the light green indicating NANs and dark green showing where we had data. Shown here is the graph of the predicted and true H values for the scikit-learn neural network throughout the summer. Here we have the same graph for the Keras model, which had an accuracy of 58.1%. And here is the graph for the SBR, which had an accuracy of about 75.3%. All these graphs were made with the full data. However, for reference, we also built an SVR model without the sonic data. We achieved about 75.5% accuracy with this model, which is not significantly different from the model with the sonic data. So we concluded that the sonic data is likely not worth the extra effort. Overall, we found quite good accuracy with most of our methods and expect these models could be quite useful in designing many of the new solar power plants which will be built in the near future.